Hello, welcome to 4.7 inverse trigonometric functions. Before we get started here, I want to talk about inverse trigonometric functions. We know a plain old trigonometric function. We know what goes in and what goes out. What goes in here is an angle measure, and what comes out is a ratio of side lengths. So we've been dealing with that for a long time. For instance, put in 30 degrees into sine, and we get sine of 30 degrees is 1/2. That's 1/2 opposite to hypotenuse. We get ratio of side lengths of right triangles. Therefore, if we're building a factory of inverse functions, inverse trig function, what would go into here is a ratio of side lengths, and what would come out here is an angle measure. And that's really important to remember at all times if we're dealing with sine inverse or cosine inverse, tangent inverse, that the values that are going in there, you know, if they want tangent inverse of 2, we might prefer to think of that as tangent inverse of 2 on 1, where this is the opposite, this is the adjacent, or this is the y, this is the x. We'd say y on x is 2 to 1. Then we're going to be building some triangles from there. So the first thing that should be a little bit troubling to us is when we talk about inverse of a sine function, we know that the sine function goes on and on and on and on and on. And therefore, sine function from negative infinity to infinity, it does not pass the horizontal line test. It's not 1-to-1. Therefore, it does not have an inverse function. So how can we have inverse functions? Well, we have to just consider a portion of the graph that's 1-to-1. And these rules talk about what portion of the graph we consider for sine, cosine, tangent, and a lot of people will try to commit these to memory, but they're going to make a lot of sense to us. Likewise here, these are all okay. You need to understand this. You need to understand these things. But if we have a good feel for what I'm about, if you have a good feel for what I'm about to go through, I think there's probably nothing here that you need to memorize. Once again, we're going to build on understanding. So, arc cosine. This is exactly the same thing as cosine inverse of 1/2. The only thing that's different would be if arc precedes it, it means cosine inverse, but it means that in this case we're dealing in radians. This does not necessarily mean we're not dealing in radians. This could be degrees or radians. You're going to see me if you're in the class or as we move on in here. I'm just going to constantly work with cosine inverse, sine inverse. I'm going to use this notation for this. So what I like about this one is we have a ratio. And that's what should go into inverse trigonometric functions, a ratio. In this case, the ratio is adjacent on hypotenuse, or this is our x on r, are in ratio 1-to-2. Now, here's some of the challenges that were presented. Cosine, x on r, this can be cosine can be 1/2 an infinite number of times. So where do we limit our answer to? So let's take a look. Just in one revolution, cosine is positive in first and third quadrant. And this is an x to r, that short x to long r, looks something like this. And of course, this would be square root of 3, negative square root of 3. We recognize these are 60-degree angles. So the question is the answer 60 degrees? Is it negative 60 degrees? Is it 300 degrees, negative 300? Or do I spin around 6 times and then just go back to here and add all of those up? So this is going to make a lot of sense to you. It's one rule fits all, and it takes care of all of this information that they feel like, hey, you should memorize this. Not me. We're going to stay as close to a 0 rotation as we can. So we're either 60 or negative 60. If there is a tie, we would prefer to go positive. So cosine inverse of 1/2 equals positive 60 degrees, or pi on 3, depending what answer they want. I suspect they want, again, because it's arc, I suspect the back of the book answer is going to be in radians, but I'm going to talk about each. So here's the deal. We stay close to 0. We can rotate either direction. We want the shortest rotation. If it's a tie, so this is a tiebreaker, and that'll be the case with cosines. If there's a tie, we choose positive rotation. Okay, so what I don't like about this is it's not given as a ratio, so I'm just going to consider this to be 0 on 1. And that is our x on r. Oh, not cosine equals, cosine of 0 on 1. So we want x on r to be 0 on 1. Forgive me for that. So when is x 0 as we rotate around? X is 0 when we get to here, or when we get to there. So our choice, if we stay close to 0 out here, is to either rotate this way 90 degrees or rotate that way 90 degrees. So cosine inverse of 0 equals 90 degrees. It's a tie, so we go with the positive 90 degrees or pi on 2. Cosine. And you see we're specializing in cosine right now. Probably shouldn't have had that many in a row that were just like that. I guess let's go over to number 8. Tangent. This is tangent inverse. I'm going to make this 1 on 1. Now, tangent is in ratio 1 to 1, of course here, 45 degrees, but also here. So our choices are 45 degrees, 225 degrees, maybe negative 135 degrees, but we stay close to 0, and this is the closest to 0. Doesn't even matter that it's positive, it's the closest to 0. So we would just say this is equal to 45 degrees or pi on 4. Okay. When is cosine negative 1? Well, again, I want to think of that as cosine inverse negative 1 on 1. So when is cosine negative 1? Well, cosine is negative 1 when x on r is negative 1. And that can happen when x is negative 1 and the radius is 1. That happens right back here, where x could be negative 1 on a radius of 1. So we're either going to use 180 degrees or negative 180 degrees. Once again, cosine is going to be that's going to be the one that ties, that we have ties. We choose the positive. So this is pi or 180 degrees. Now, if I have cosine inverse of 0 or 1 or negative 1, I might be really tempted to think about the graph of cosine. And we want to say, when is cosine negative 1? Well, cosine's negative 1 right here at pi or right here at negative pi. When is cosine 0? At pi on 2 or negative pi on 2. When is cosine 1? At 0 or 2 pi, etc. So those are really nice values. Those are quadrantals when sine and cosine are 1, negative 1, and 0. Okay, cosine inverse negative 2 or negative 2 on 1. That means I want x to r to be in ratio negative 2 to 1. When can a side length of a right triangle be bigger than the hypotenuse? It can't be. No solution. Okay, I believe by the time you're looking at this video, we would know, if you're at this level of trigonometry, we could recognize perhaps this guy has been rationalized. This would be negative 1 on square root of 2. So we want a y on r ratio to be negative 1 on square root of 2. You can work with it this way, but I recognize this as a 45-45, 90 right triangle. So when is sine negative? Here, we're negative 1 on square root of 2. And here, sine is negative 1 on square root of 2. So we either want this rotation or this one. Well, we want the one that's closest to 0. So that is negative 45 degrees or pi on 4. Cosine inverse of negative square root of 3 on 1. I want that to be a ratio. What ratio is it? X to r is negative square root of 3 on 1. But once again, this is bigger than this. When is x bigger than r? Never. No solution. And sine inverse of, I like derationalizing this, 1 on square root of 2 means we want to build a y on r of 1 on square root of 2. If this is a positive value in any inverse function and the triangle exists, and we can get there on a rotation, we can get in this case, the y on r values on a rotation, y is less than r, then we're always in the first quadrant because we want to be close to 0, but in the first quadrant, but positive if it's a tie. So this would just be a 1 square root of 2, 1 triangle, so 45 degrees or 1/4 pi. Okay, so these are just calculators. They don't ask us, or they don't tell us, do we want radians, do we want degrees? Again, this would be a radian measure. I suspect they're looking for radians because they're asking for the nearest hundredth, and a hundredth of a degree. That would be very, very precise. Let's go clear here. So let's take a look at these for a moment. I'm going to find the radian measures first. Just putting in a spot for the radian measures. So I'm going to go into mode, go radians, and second quit. And then I'm going to go cosine inverse 0.28. Pretty easy. And that is 1.29 approximately. And then second, sine inverse of negative 1.3. And, oh, there's a no solution. And we might have realized it since sine itself runs between negative 1 and 1, 1 and negative 1. Sine inverse, we can't put in anything unless it's between negative 1 and 1. So no solution. And tangent, second tangent inverse 5.9 is 1.40. And now I'm just going to go through and find the degree measures and take a look where we're at here. So mode, degrees, second quit, and I'm going to use second entry to get back to cosine. And you see that's a degree measure. We set our calculator in degrees, so that first value would be approximately 73.74 degrees. Sine's still not going to exist. And second entry, tangent inverse 5.9, that must be a degree measure. Calculator's in degrees, 80.38. Okay, so that should be pretty straightforward. It's just a matter of degrees, or like if I was solving for theta here, I would probably, since it's in a right triangle, I probably would talk about degrees. It's gonna be pretty clear for you when you quiz test. Sometimes I might ask for both, but it'll be pretty clear, or it'll specify what we should be working with. Use an inverse trigonometric function to write theta as a function of x. So I want theta as a function of x. And we might be able to get there in one step, but that would be pretty good. I'm going to go back to just SOHCAHTOA talk. I've got an angle, I've got an adjacent, I've got a hypotenuse. So we could say cosine, it would be adjacent hypotenuse. Cosine of theta is, I'm going to leave a space here, you'll see why, 4 on x, adjacent on hypotenuse. But I want to get rid of cosine. I don't divide away cosine. It's a function. To cancel a function, we take the inverse of both sides, and we get theta, cosine inverse cosine cancel, we get theta equals cosine inverse of 4 on x, and of course that's theta in terms of x. You tell me what x is, I put it here, and you've got theta. Give me this value, and I'll find theta for you just by putting it right there. Okay, so let's see if we can synthesize that and do this in one step. Opposite, adjacent, tangent. So we're used to doing this. Tangent of theta equals this on this. Therefore, tangent inverse of the ratio, the tangent ratio is x plus 1. Remember, that's what happens. We talked about that before we even started on here. We put the ratio of side lengths into inverse trig functions. Opposite on adjacent 10 equals theta, or better yet, theta of x. So theta is now a function of x. All right, let's take a look. Find the length of the third side of the triangle in terms of x. So the third side of the triangle here, I'm going to need to borrow some space over here. The third side, if I call this side a length of a, I know that x squared plus a squared equals 3 squared, or a squared equals 9 minus x squared, or a algebraically would be plus or minus the square root of, but we're not going to have a negative value here. We need a to be positive, so it's just positive square root 9 minus x squared. Don't get trapped into thinking we can just make that 3 minus x. 3 minus x times 3 minus x does not equal 9 minus x squared. So this is ugly, square root 9 minus x squared, but that's what it is. Then it says, find the length, then find theta in terms of x for all three inverse trigonometric functions. So theta in terms of x equals, well, let's see, it's sine inverse of, what's the sine ratio? Y on r. Theta in terms of x is cosine inverse. What's the cosine ratio? X, or adjacent on hypotenuse, square root of 9 minus x squared on 3. And theta as a function of x is tangent inverse of opposite on adjacent, x on square root 9 minus x squared. And if you just feel the need to rationalize that, you're welcome to. I suspect the back of the book wouldn't even rationalize that one. Okay, let's take a look at 52. I'm going to call this r, or you could call it h for hypotenuse if you choose. But here's what we know. We know that r squared equals 3 squared plus x plus 2 squared, or r squared equals 9 plus FOILed x squared. I'm going to get 2 x's and 2 x's, and I'm going to get a plus 4. Or r squared, r equals, this is still r squared, excuse me, r equals the square root of x squared plus 4x plus 13. And again, it's not plus or minus because r is going to be a positive value. So square root x squared plus 4x plus 13. It's messy, but that's what it is. So sine, I didn't want to do that. Theta of x equals sine inverse. I really boxed myself in with that mistake. I'm going to redo that. And theta of x equals sine inverse of y on r, or x plus 2 on big square root of x squared plus 4x plus 13. Let's see if I can fit these. Theta of x in terms of cosine, I'm not going to be able to, is 3 on big square root of x squared plus 4x plus 13. And continued over here, theta of x in terms of tangent inverse. Tangents ratio is x plus 2 on 3. Okay, so there's our 3 solutions for that one. Okay, some of this is going to seem like, I'm going to go through a couple of these problems and you're going to say, boy, I can do this without even any thought. And sometimes you can get away with that, but sometimes there's a problem. We're going to discover over the next couple of days when we get some problems. But for right now, we're going to take this, we're going to be real careful with these. Tangent of tangent inverse of 25 on 1. This is a ratio. It's going to become an angle. But this is the y on x ratio, 25 to 1. And tangent is positive in the first third quadrant, so we would choose first, it's closest to 0. So I want a y on x, this isn't even near scale, y on x of 25 to 1. And sometimes we want the hypotenuse. But here's our angle theta. If I think of this as theta, then tangent of theta is just tangent of this angle right here, which is 25 on 1. And I certainly understand why you say, well, then I can just do, these are just going to cancel each other. There are some times when tangent inverse of tangent doesn't become the same, doesn't become the argument. If there's an inverse trig function out here with its trig function in there, you got to be really careful with this. So for right now, we're going to build triangles. Okay, what goes into inverse functions? Ratios. So when I get a decimal, I'm going to write it as a ratio. Sine inverse of, before you were ever allowed, forget about the negative for a second, before you were ever allowed to call this 0.1, you would have called it 1/10. So 1/10. Therefore, I want to build a triangle where sine is negative here and here, as we all know. This is the y on r ratio, -1 to 10. There's our angle theta. I'm thinking this of just sine of theta, because that's what inverse trigonometric functions are. They're angles based on the ratios. So what's sine of this angle? Oh yeah, it's -0.1 or -1 on 10. It didn't change. So you're going to think, well, that's fine. You're going to look at this one. We're going to say, well, this must be -2. Well, this is cosine inverse of -2 on 1. We want x on r to be in ratio -2 to 1. When is x bigger than r? Never. No solution. Okay, here's a dangerous one. Don't inverse trig functions just turn things into what they were? Doesn't this just undo sine? Well, let's take a look. Sine of 4/3 pi. 1/3, 2/3, 3/3, 4/3 pi. We're right here. We've got a nice 30, 60, 90, -1, 2, -square root of 3. So this is now asking for sine inverse, arcsine, sine inverse of this angle. Well, that's what it was doing. That's what it was doing before. So I want sine inverse of sine of that angle. Sine of that angle is y on r. Sine of this angle, y on r, -square root of 3 on 2. So it's saying, when is sine -square root of 3 on 2? And yes, it is at 4/3 pi, but we want to be close to 0. Sine is also -square root of 3 on 2 right here, and that's closer to 0. That's just -60 degrees or -pi on 3. So we got to be careful. Notice that didn't end there, and I'm telling you right now, there are going to be people on quiz tests that are going to make that mistake. It's so tempting because we'll have a number of problems. Oh, tangent of tangent inverse, no problem. Sine of sine inverse, no problem. But then you might have something where there's no solution, or we just get thrown to a different angle. All right, let's take a look at this one. Cosine of 3/2 pi. 1/2, 2/2, 3/2 pi. This would be like the point 0, -1, where r is 1. Cosine is x on r. This is just asking cosine inverse of 0. So this is, when is cosine 0? Well, it's 0 here. It's 0 here at 0, 1. It's 0 spin 1,000 times around and then go to there. But it's a toss-up between this, which ones are close to 0, and this. Remember, cosines are the troublemakers as far as we got to go to the tiebreaker. The tiebreaker is rotate positive if we're the same distance. So this is 90 degrees or pi on 2. Once again, if we have an inverse trig function outside and the same trig function inside, that is danger time. This one actually a little bit more work involved because we're going to have to do some Pythagorean, perhaps. Perhaps when they're backwards. In this case, truthfully, we're not going to have to. But when you have a mixture of, not tangent, inverse, and tangent, if these were backwards. Anyway, let's take a look at this. Let's go to 3/4 pi. 3/4 pi right here. This is -1 by 1 by square root of 2. So this is cosine inverse of tangent of this angle is y on x, 1 on -1. So we want an x to r ratio of 1 to -1. When can the side length be as long as the hypotenuse? It can't. However, when it's the same length, that's quadrantal. I want x to be -1 when r is 1. And that happens right here at -1, 0, r is 1. So it's either 180 that way or 180 that way. We choose positive. 180 degrees or pi. Okay, here's the Pythagorean thing I was bringing up on 64. Find the exact value of the expression. Use graphing utility to verify the results. Hint, make a sketch of the right triangle. So we need sine. We want to know when sine is positive 24/5. Well, sine is positive in first and second quadrant, so we're going to build this in the first. That is a y on r in ratio of 24 to 25. And that is a Pythagorean triple, but you can check it. It gives us 7 here. So this is theta. I don't know how big theta is, but I'm supposed to find cosine of theta. If I know the side lengths, I've got it. Cosine of theta is adjacent on hypotenuse, or x on r, is 7 on 25. Just got to make sure we build these in the correct triangle. So here, tangent inverse, I'm thinking of this whole thing as just an angle. That's what inverse trigonometric functions are. They're angles based on ratios. I know I've repeated it, but it's a really important concept. I need y on x to be in ratio of -12 to 5, excuse me. And tangent is negative here and here. All students take calculus. They're all positive here, tangent's positive here. So I could either build a triangle here or build a triangle here. I'm not trying to represent that as a 45. I'm just building a triangle. But we stay close to 0. Big key in this section. That's y, -12 on x, 5. That's a triple. This is 13 Pythagorean, and we want cosecant. And I remember cosecant this way. Cosecant's reciprocal of sine. Sine's y on r. We want r on y. And r on y, we get 13 on -12. So -13/12. It could be 13 on -12. Okay. If I think of this as theta, I want to build theta. Tangent, once again, is negative here or here. We stay close to 0. This is y on x, 3 to 5, and there's the negative. And we might be thinking 4, but of course that's the hypotenuse. 3, 4, 5s, the hypotenuse would have to be 5. So 25 plus 9, 34. This side is square root of 34. We want secant, reciprocal of cosine. Cosine is x on r. We want r on x. And r to x, that ratio is square root of 34 to 5. And finally, 72, cotangent of arctangent. I'm thinking of this as an angle. If it's positive ratio, we're going to build it in the first quadrant. Our choice for tangent to be positive first or third, but first always trumps the other quadrants. So this is y5 on x8. And normally we'd be doing Pythagorean here, but take a look. Here's theta. We just want cotangent of theta, 8 on 5. Okay, now, important announcement here. I got to grab my sheet, take a look at this. This homework set doesn't include everything I want on it. We're 17, actually we go 17, it's a much bigger assignment, sorry about that. We're going to go 17 through 31, but not really through 31. We're actually going to take that all the way through, looking at my book right now, all the way to 79. It's on the website now, fixed that way. But that just means you'll get some more time to work on it. But those are concepts we definitely have to know going forward into calculus. So 1 through 4, 5 through 11 odds, 17 through 79 odds, and I must really like 101 to make that big of a jump for just one problem. So let me know what I can help you with, and good luck.